Four solutions for Math 211. First problem has to do with numbers in different bases. You're asked to essentially fill in the blank. If you have this number ABC in base 16, what is that in base 10? And I guess the first thing you need to know is that A, B, and C represent the base 10 concepts of 10, 11, and 12 when you're in base 16. The next thing you need to know is that when you're in base 16, the furthest right number that you write, the way we thought about it or described it in class, it's the number of single donuts that you buy, whereas the next digit represents the number of boxes of 16 donuts, 16 to the first power if you want, and the next digit would be 16 to the second power. So really, what's going on with this problem, and then it continues if you had more than 3 digits, but I only have 3 digits, so I can stop there. What's going on with this problem is I have C in this column, but C is just 12. And I have B in this column, but B is just 11. And I have A in this column, but A is 10. So the total number of donuts I have is 16 squared, which is 256, times 10, plus, maybe I'll write that out, 16 squared times 10, plus 16 to the first power, times 11, plus 16 to the 0 power, which is 1, times 12. And as I was saying, that's 256 times 10, plus 16 times 11, plus 1 times 12. And 256 times 10 is 2,560. 16 times 11, well, 16 times 10 is 160. And 16 more than 160 would be 176. And 1 times 12 is just 12. And if you add up these three numbers, let's see, this and this give me 188. Okay, that's added up a long way. 0 plus 6 plus 2 gives me an 8. 6 plus 7 plus 1 gives me 14, so I'll write the 4 and carry the 1. 5 plus 1 plus 0 is 6, but remember I carried a 1, so I got a 7. And then I got the 2,000. What I'm figuring out is that in base 10, this number would be written as 2,748. This next problem is similar, except now you're working backwards. In this problem, you have 4,350 donuts you want to buy, and you have to figure out what size the boxes should be. And to do that, I'm going to set things up kind of like I did above. I got single donuts, I got donuts that come in boxes of 16, donuts that come in boxes of 256, and in this case I might have more than 3 digits, so I better figure out what 16 to the third power is, just in case it's 4,096. And I can stop here because 16 times 4,096 would be such a huge box I'd get way more than 4,350 donuts, so I don't even need to consider it. Let's make these a little smaller so I got room to do everything. So all I got to do is fill in right here. So how many boxes of 4,096 you want? Well, just one, right? And so I would say 4,350 minus 4,096 is 354? Nope. 254 maybe? The 4,000s go away, and I'm almost taking away 100. If I was taking away 100, I'd be left with 250. But I'm not quite taking away 100. I'm taking away 4 less than 100, so I'm left with 254. Okay, 254, that leaves me with no boxes of 256. And so I'm going to have a lot of boxes of 16. How many boxes of 16? Well, if I do 16 going into, well, maybe I'll just write this. If you divide 254 by 16, you get a big number, 15.875. So I'm going to want 15 boxes here. 15 times 16, or maybe I'll write this here, 254 minus 15 times 16. Let's see, 10 times 16 is 160. 5 times 16 is 80. I think this is 240. And so I'm getting 240 donuts out of my size 16 boxes. I want to subtract 240 here. And what that means is I need 14 more donuts. If I need 14 more donuts, I have to buy them in singles because the smallest box is size 16. So this is my answer in some sense, although it's not the final answer because I can't write 101514. You would think that that meant 4 singles and 1 box of 16, 5 boxes of 256, 1 box of 4,000, and so on. So what I got to do is I got to convert any numbers that require more than 1 digit, like 14 and 15, into their base 16 symbol. And I have their base 16 symbols above. So really I have E here, I have F here, I have a 0 here, and a 1 here. So my answer will be 10 FE. This problem, let's see. It's either really hard or really easy. No, that's not true. It's either really hard or you have to be clever. And if you're going to be clever, the way you do it is you notice that the box sizes in base 8 all exist in base 2. What I'm saying is if I'm buying donuts at a base 8 shop, I can buy singles, or I can buy boxes of 8, or I can buy boxes of 64, or I can buy boxes of 8 to the 3rd power, which my calculator tells me is 512, or I can do 8 to the 4th power, which my calculator tells me is 4096, or I could do 8 to the 5th power, which maybe I went a little bit overboard with these numbers. That's 32,768. Fine. So at a base 8 shop, I was buying one of these, 0 of these, 1 of these, 1 of these, 1 of these. I got 1 of these, 1 of these, 0 of these, 1 of these, 1 of these, 1 of these. So what does that have to do with a base 2 shop? Well, at a base 2 shop, my options are I can buy single donuts, I can buy boxes of size 2, boxes of size 4, boxes of size 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. I'm going to screw one of these up soon. 8,180, 92, 8192. I think that's right. Double that. Good Lord. 16, 384, I think. Then if you double that, you get that. Yeah, that looks about right. 32,768. Anyways, my point is all these red box sizes are what I have when I'm in base 2. And the reason it's important is if you note, every box that I bought in size green, I could have bought in size red. In other words, I could just buy one of these, and one of these, and none of those, and one of those, and one of those, and one of those. What about the rest of the box sizes? You don't need them because you already got all your donuts. So just throw zeros everywhere else. And then figure out how the hell to write that number. Well, let's see. The last 3 digits I have are 001. That's these 3 right here. The 3 prior to that were 001 also. The 3 prior to that, were these 3, which were 000. The 3 prior to that were 001. The 3 prior to that were 001, and the leading digit was a 1. So this mess right here would be the way I'd write that number in base 2. Apologies to anybody who took this and converted to base 10 and then took that that big number and converted that into base 2. I guess you could do it with the calculator, but it sounds like a pain. All right, moving on. Another base problem. Damn, I really went overboard with these base problems. How many base 5 numbers have exactly 10 digits? Don't count any leading zeros. Note. There are 5 base 5 numbers that require 1 digit. Specifically, the numbers 0, 1, 2, 3, and 4. There are 25 base 5 numbers that require 2 or less digits. Why is that true? Maybe because buying anywhere from, doesn't say from, try again, from 0 to 24 donuts would only require, I don't know, singles and small boxes. And so on. There are 125, 5 to the third power, base 5 numbers that require 3 digits or less. So maybe from here, I can draw the conclusion. There are 5 to the 10th power, base 5 numbers. That require 10 digits or less. And there are 5 to the 9th power, base 5 numbers. That require 9 digits or less. And if this many require 10 or less, and this many require 9 or less, the difference in those two require exactly 10. So 5 to the 10th minus 5 to the 9th require exactly 10 digits. I'm not going to bother calculating that number. You can if you feel like it, but I'm going to leave it just like that. All right, moving on. Relations and functions. You're given this relation on a set and asked if it's reflexive, symmetric, and transitive, and or transitive. Let's see, reflexive. Nope. Why not? Because, I don't know, 2, 2, for example, is not in my relation. To be reflexive, it needs to have 1, 1, 2, 2, and 3, 3. There needs to be an arrow from every single element to itself. There's no arrow from 2 to 2. It's not reflexive. Symmetric. I think it is symmetric. Yes. These don't need exclamation points. Because for any element AB in R, the element BA is also in R. And I guess you just go through and check. Here's 1, 2. Oh, good. Here's 2, 1. Here's 1, 3. I got 3, 1. Here's 2, 1. I got 1, 2. Here's 2, 3. I got 3, 2. Here's 3, 2. I got 2, 3. Here's 3, 1. I got 1, 3. Good enough. And here's 1, 1. I got 1, 1. Transitive. No. You're welcome. I think I told you that you should thank me if I make something that's not transitive, because it's a hell of a lot easier to show something is not transitive than to show that it is transitive. Note that I do not have the element 2, 2 in this set. Remember that from up here when we were talking about reflexive? The element 2, 1 and the element 1, 2 are in this relation, but the element 2, 2 is not. So it's not transitive. That's it. Our last problem on relations actually changed a little bit. So the relation, the way it's now defined, is two people, which are the elements of our set, are related if they have the same biological grandfather. If they share a biological grandfather. I might word that a little bit more carefully. At any rate, if they share a biological grandfather, they're related. Is this set reflexive? Sure. I have the same biological grandfather as I have. I share a biological grandfather. In fact, I share both of them. Reflexive, question mark? Sure. I have same everyone. I shouldn't say I because that implies that you only need one of them. Yes. Everyone has the same shares grandfather with themselves. It's hard to write. It's been a long day. With themselves. Maybe that's 2 words. Frankly, I don't care. Symmetric. Yeah, I guess so. Yes, if A and B share a grandfather, and so do B and A. What about transitive? Transitive is always the tricky one. Transitive. No, I don't think so. Okay, maybe I can do this with a diagram. Here is person A, and here are their parents. Sure. Mom, dad, and grandfather. And there's a grandfather over here also. So this grandfather might have had multiple children, so not just dad, but they might also have this guy, who I guess would be person A's uncle. And person A's uncle might have had a child. Maybe that person is person B. Fine. Person B also has these 2 grandfathers, their uncle's dad and or not their uncle, person A's uncle's dad, person A's aunt's dad. Whew. And person A's aunt's dad might have had another child here. Anyways, this is the picture. Transitive, no. A and B share grandfather. Maybe I'll call this grandfather 1, 2, and 3. A and B share grandfather 2. B and C share grandfather 3. But A and B and C don't share a grandfather. Okay, it's time to stop. I'm going to stop this video.